So if you want to put something like this in MATLAB, my favorite way of writing it is to say that this is 1.194 exp parentheses, and then you're putting this in the j theta form, right? So this would be j times 114, but that's in degrees, so you also have to multiply by the conversion factor, right? That there are pi radians per 180 degrees, so just multiply by pi, divide by 180, and that's how you would type that in. I find that to be the quickest and easiest way. And then this should be a multiplication symbol right there too. Right? That's the format I like. If you really like one of the other formats though, no problem, right? I just like this because I'm not typing in any special functions. If you use the pole to cart function, it defines the x and the y, the real and the imaginary parts separately, and they're in like an array, and I just don't like having to deal with that. I'd rather get all combined into one complex number. Keeps it stored in my brain better, right? So that's the method I like. You can choose a different one if you like. Okay. Next topic, superposition. Now, superposition is really handy for us because it actually gives us a little bit more power, if you will, in analyzing our circuits than we've had in Chapter 9. Because superposition says I can deal with each one of my independent supplies separately and then add them together to get my final result, right? So since each one of my supplies acts independently, each one of my supplies could have a different frequency. So this is the way we can start to deal with more than one frequency acting in our circuit. And in fact, we'll expand upon this idea as we move into full frequency domain analysis, and we'll actually be able to kind of come full circle and realize that even when we're dealing with lots of frequencies, a whole range of frequencies, we really break it down and deal with it with superposition. So this, as a fundamental principle of the circuit's behavior, is a very powerful topic. So for now, we're going to just deal with maybe one or two different frequencies. And it's not that difficult. And then, again, like I say, we'll expand upon it, but we'll have some better math tools to help us do that, especially if we get towards Chapter 14 and on. All right. So we're going to deal with the separate phasor circuit for each frequency, and we're going to solve those independently, and then we're just going to add them in the time domain. We're going to add all of those pieces up and get a total result. So, again, it's always nice to look at one straightforward example to see how to do this. So, in Chapter 4, if I had been dealing with this and I asked you, okay, what is VO here? And this was just 30 volts and this was just 2 amps. We could have done that extremely easily, right? We could have done it in your head pretty much, because you could have said, well, let me see what the effect of this voltage supply is. I'm going to turn this off, and if this was just resistors, right, or something like that, you would just look at that and you would say, oh, well, that's like a voltage divider. And I would find VO due to this voltage supply. Then I would turn this off by short-circuiting it and turn this on, and I would see, well, how much current flows through here? Well, that's like a current divider, right? It's got 3 elements in parallel. The current can flow into each of them, so how much flows into this middle one? And I would have figured out the voltage then that resulted from that current, and I would have solved the problem. Well, that's if those are all resistors and these are DC. But guess what? They're all impedances, and this is just phasors, right? So it's not a big deal, except that I need to redraw the circuit and recalculate the impedance values with the different omega for each of the supplies. So let's deal with our first. We're going to deal with this voltage supply first. All right. So I'll redraw my circuit. And again, a current supply, we turn it off by opening the circuit, right? Broken wire, no current can flow. So current supplies are off when it's an open circuit. So it's just not even there, right? And now I'm going to look at this. I'm going to say, okay, I'm dealing with this 30-volt power supply. It's 30 sine of 5t. Okay, I need to write down omega is 5. And again, this we can go back to that same method we used for the previous, where even though we normally define the phasor as a cosine, since we only have a sine present, why bother with that extra phase shift? We're just going to leave it as a sine. And so we're going to call this 30 with an angle of 0. Right? There's no defined phase. So 30 angle of 0 when we're dealing with it as a sine. And then we need to figure out what our components are, knowing that omega is 5. Well, the 8 stays the same for the resistor. The capacitor, though, 0.2 farads, again, I'm looking at this as negative j over omega c. So negative j over 5 times 0.2. Right? I think I can do this one. Right? Because 5 times 0.2 is 0.1. 1 over 0.1 is 10, right?
No, it's just 1.
Just 1? What?
1 over 0.1 is 10.
Yeah.
Over 5 times 0.2.
Oh, you're right. I did my decimal wrong. See? This is why I don't do it in my head at all. Darn it. It got me. You're right. So, because 5 times 2 is 10, and that's only 1 decimal point, so it's a 1. Sorry. All right. That's even easier than I thought. Perfect. So negative j. Okay. Darn. I'm not kidding.